The uniform acceleration produced in a freely falling body due to the gravitational force of the Earth is called the acceleration due to gravity. Suppose an object of mass m is released from a distance r from the center of the Earth. Let m be the mass of the Earth. Then, using Newton's law of gravitation, we have F is equal to g multiplied by m multiplied by m divided by r squared, where g is the constant of gravitation. Acceleration is given by the formula acceleration is equal to force divided by mass. Therefore, acceleration is equal to F divided by m, which is equal to 1 divided by m multiplied by F divided by 1. Therefore, acceleration is equal to g multiplied by m multiplied by m divided by m multiplied by r squared, which is equal to 1 divided by m multiplied by g multiplied by m multiplied by m divided by r squared. Therefore, acceleration g is equal to g multiplied by m divided by r squared. This is called as acceleration due to gravity. From the above relation, acceleration depends on m, which is the mass of the Earth, and r, which is the height of the object from the center of the Earth. It does not depend upon the mass of the falling object. Thus, acceleration due to gravity is same for all freely falling bodies. Students, now let us proceed further into the value of g and see its variations. The value of g on the surface of the Earth. The acceleration due to gravity near the surface of the Earth can be calculated. The mass of the Earth is 6 multiplied by 10 raised to the power of 24 kilograms, and its radius is 6.4 multiplied by 10 raised to the power of 6 meters. Substituting these values in the equation, we get g is equal to 6.67 multiplied by 10 raised to the power of minus 11 multiplied by 6 multiplied by 10 raised to the power of 24 divided by 6.4 multiplied by 10 raised to the power of 6, the whole raised squared. Therefore, g is equal to 9.8 meters per second squared. The acceleration due to gravity is always directed vertically downwards, that is, towards the center of the Earth. If an object is thrown vertically upwards, its motion is in the opposite direction of gravity, and hence the acceleration is in the opposite direction. That is, its motion is retarded by the acceleration due to gravity. Therefore, its velocity goes on decreasing and finally becomes zero at some height, after which the object begins to move vertically downwards under the effect of the acceleration due to gravity, due to which its velocity goes on increasing. Variation in the value of g. Let us see the variation in the value of g with respect to altitude. The value of g decreases with altitude because the distance from the center of the Earth increases. As we go to some height, h, above the surface of the Earth, the value of g changes by 1 divided by the sum of r and h the whole squared, where r is the radius of the Earth. The value of g at different altitudes is shown in this table. At the mean Earth surface, where the altitude is 0 kilometers, g is 9.83 meters per second squared. On the tip of Mount Everest, where the altitude is 8.8 kilometers, g is 9.80 meters per second squared. At the maximum height reached by manned balloon, where the altitude is 36.6 kilometers, g is 9.71 meters per second squared. At the Space Shuttle orbit, where the altitude is 400 kilometers, g is 8.70 meters per second squared. At the communication satellite, where the altitude is 35,700 kilometers, g is 0.225 meters per second squared. Let us see the variation in the value of g with respect to depth. If one goes deep inside the Earth, the value of g decreases. However, the above formula for g is not applicable inside the surface of the Earth. At the center of the Earth, the value of g becomes 0. Thus, we can conclude that the value of g is maximum on the surface of the Earth. It decreases when we go above or below the surface of the Earth. Let us see the variation in the value of g with respect to the shape of the Earth. We know that Earth does not have a perfectly spherical shape. It is slightly flattened at the poles and bulges at the equator. Therefore, the radius of the Earth at the poles is less than that at the equator. It is found from experiments the value of g is different at different places on the surface of the Earth, ranging from a maximum value of 9.83 meters per second squared at the poles to a minimum value of 9.78 meters per second squared at the equator. However, for all practical purposes, the average value of g at or near the Earth's surface is assumed to be 9.8 meters per second squared.